We just did the average case efficiency for 7 elements array. Yeah. Let me change the color. Yeah. All right. That is the answer. Okay? So you know how to calculate. All right. Example. Now I want to talk about the general result. With n elements, any number, n elements. If we still calculate average case for arbitrary n, okay? In homework assignment, I will give you those questions. Yeah. N could be like 25, 37. I just pick some, not too big numbers so you can handle. Yeah. If too big, you need to do too much work, right? Yeah. So that question I will give you in the homework assignment number 2. Yeah. But here we want to look at the general case. Yeah. The general case for any n. What's that number? Here I do not give you the exact formula because the formula calculated. Yeah, although could be calculated. All right. So here what I like to do is the average case efficiency for binary search with n elements. That result. Okay? All right. That result, let's look at this example first. For this example, you know the worst case, right? The worst case number, let's say the worst case number equals 3 comparison, right? Yeah. Here the average case is this one equals 2 and 7/3, right? Yeah. Look at the difference. Compare this number, the difference with the worst case. Less than 1, right? The difference is less than 1. So that means the average case efficiency, that number comparison is very close to the worst case. How close it is? Less than 1. From this example. Also true for the general n case. Also true for the general n case. Okay? So with n elements, let's say number of comparison. Okay? All right. Or let me use the binary search. Okay? Yeah. Binary search, if I use B sub A to represent average case for the binary search, that number. Okay? All right. Another one, I use B sub W, worst case binary search. So we know worst case is greater than the average case, right? That number, the difference here, we use worst case number minus binary case number, that number is less than 1. That's the general result. Okay? Yeah. So close to the worst case. 1. No? Yeah. It can be proved. Yeah. Although the calculation a little harder, that can be proved. The formula, you can write a formula estimate, inequality. Yeah, you can see that. All right? Yeah, but here I just give you this result because you may see some questions about this in your assignment or test. Okay? So I already give it to you. Yeah. So you will see somewhere. Okay? Yeah. All right. So that's this one. Yeah. Next one. B.4, Introduction to Selection Problem. we did a few selection problems already. Okay? Here I want to talk about the general selection problem. We did some special. Minimum, maximum, second smallest, second largest, and both maximum, minimum, right? Yeah, we did several versions of the selection problem. Yeah. Median, yeah. Median, but we haven't done much. We talk about a little bit. Yeah. Median, a little bit. Yeah. Last question, midterm, finding the median, also the selection problem. Okay? Yeah. Here I want to talk about the general selection question. Yeah. But the algorithm is very complicated, so I do not plan to talk about the whole algorithm details. I just talk about the basic ideas and then give you results. Yeah. So that's what I want to do about this general selection question. Given an array and a positive integer k, this k number, some integer somewhere between 1 and n, one of those numbers. Yeah. How to find the kth smallest element? Now, that's we call a selection problem. Okay? Yeah. K is given. Yeah. If k corresponds to the element in the middle, that's the median. Okay? Yeah. So we know how to calculate. So that median. Here, we also call this k, the element corresponding to this k, the kth order statistic. Yeah. That name. Okay? All right. Another name, rank equals k. Yeah. We can also call, this element has rank k. Okay. Yeah. Just some term. Okay? All right. Yeah. All right. Let's do analysis. Yeah. Given an array to solve the selection problem, the data is unordered. Otherwise, if data is ordered, it's trivial, right? Yeah, trivial. You can get any element of rank k immediately. Yeah. But here we assume data is unordered. Then it's not easy. Yeah. Then it's not easy. Okay. All right? Yeah. Should we solve the array first? Here, there is one question. Yeah. Because many people, they feel they can solve the array first, then they can find any element with rank k easily, right? Yeah. But the question is, we know sorting is quite expensive. Are you willing to pay that much to sort the whole array? Yeah. Sometimes you are willing to pay, sometimes you are not willing to pay. Okay? Yeah. It depends on how many times you want to do the selection problem. How many times? Yeah. If you need to do many, many times, then it's better to sort the array, right? Yeah, because if you want to do it repeatedly, large number of times, then you sort it first, it's better. But if you only want to do small number of times, then sorting is not a good idea. Yeah. Because you need to do too much work. Okay? If a small number of selection problem you want to solve, then you need to use a different method. Yeah. Here, let's talk about that different method. Divide and conquer. Yeah. Yeah. The title of this module, divide and conquer. We solve it. Yeah. All right, so here, because the sorting cost, big theta of n log n. Yeah. That's a, relatively fast sorting algorithm. Not a insertion sort. We do not we do not feel insertion sort is fast enough for the general case. Yeah. So later we will see a few algorithm, merge sort, quick sort, and heap sort. They can all get big theta of n log n efficiency. Yeah. Quick sort is the overall best. Overall best. Okay? Yeah. Yeah. So for the remaining of the semester, we will cover these 3 more sorting algorithm. Yeah. All right. How do we divide the problem? Now, related to divide and conquer, but how do you divide? How do you split the array into 2 subarrays? And after one comparison, you want to throw away one of the subarrays, similar to the binary search. Similar to the way you do the binary search, but binary search you work on ordered array. Here we work on unordered array. That's the main difference. Yeah. That part much harder than the binary search. Binary search, very little work. Each time after you do comparison, you throw away. You only need to do very little amount of work. But here you need, because the array is not sorted. If you want to throw away one subarray, you want to make sure that subarray does not contain the element to be searched for, right? You don't want to throw away the element to be searched away, right? Yeah. But how do you make sure the subarray that you cut off, you drop it, cut off, does not contain the element to be searched? You need to do a lot of work, okay? You need to do, comparisons. Yeah. Idea. Yeah. Here I talk about general idea. The details, if you are interested, you can look at a textbook. Yeah. For this class, we do not require that. Okay? Yeah, pretty complicated. Yeah. But if you want to try, yeah, you can understand it. Yeah. Here I talk about general idea. Divide the problem into 2 subproblems. The question is how to divide. Yeah. Somewhere in the middle, yeah. So we want somewhere in the middle, the best we can. The point that we divide 2 subarrays should be as close to the middle as possible, but we do not want to use too many comparisons to find that point, right? Yeah, otherwise, too slow. Okay? Yeah. All right. Drop one of the subproblems. But when you drop, you want to make sure it does not contain the element with the given rank number, K. That's important. Okay? Convert the original problem to one of the subproblems. Because if you can drop one of the 2 subarrays, you reduce the problem size, then you do next round, divide and conquer. Another round, divide and conquer. Yeah. Similar to the binary search. And eventually, you find that element. That simple idea. Yeah. All right. Yeah. But you may need to do, so here, kth order statistic. The element we want to search, that one, kth order statistic. So we want to locate a range for it. We want to locate a range covering that element. Yeah. All right. Yeah. All right. Rth order statistic. Yeah, because here there is a property. Yeah. We will see that. Yeah. Yes. Order. the same element, that same position, can you also count from right? From right. If you count from right, it's the R number. It's from K, R number. Okay? Yeah. All right. Two cases. Eliminate from left end. Sometimes you do elimination on the left subarray. Sometimes you do elimination on the right subarray. Yeah. Two cases. Yeah. Okay. Yeah. All right. Yeah. So when you split an array, yeah, containing the element of that kth order statistic. Okay. All right. So you want to estimate the location of this element from two sides, left side, right side, symmetric. Okay. Symmetric. Yeah, you want to do the work symmetric. Okay. Yeah. All right. Yeah. So left side, right side. Yeah. All right. And you want to make sure you can exclude certain size small subarray from the left side without containing the element, your kth order statistic. At the same time, you will also want to exclude from the right side certain size of the subarray, and this subarray does not contain this, target element. Yeah. Target element. How to do it? Is it possible? Is it possible how to do it? Yeah. Here, I can describe a simple idea to tell you it's possible. Okay? It's possible. Let me describe a simple idea. Okay? All right. Just the main idea of the selection problem, the solution idea. Okay. All right. Here, draw a simple diagram here to show you the main idea so you can understand why we can exclude left subarray and the right subarray without containing our target element. Yeah. All right. Let me consider the example for 15 elements. 15, this number, because I can group it into 5 groups. Each group has 3 elements. So I draw these 15 elements in this way. 15 elements in 5 groups. 5 groups. Each group, 3 elements. Okay? Each group, can we sort 3 elements in that group? We can sort it, right? The top one, largest, middle one, median, smallest one, bottom. We sort it. Each one with 3 elements, we sort it. We use 3 comparisons. Okay? Yeah. We sort only 3 elements for these 5 groups. Okay? Yeah. Because we try to, estimate these 2 subarrays we can exclude. Yeah. All right. Yeah. All right. Yeah. Actually, here I'm talking about. So we can use the median case. Okay. Here I talk about median. Yeah. Actually, if it's not median, later we can also modify it from this one. Yeah. All right. Then after we sort these 5 groups, we want to look at the 5 medians of the 5 groups. There are 5 medians of 5 groups, right? Yeah, 5 medians. Okay. Next, we want to use recursion to find the median of these 5 elements, right? Recursion. Yeah. Yeah. Because our original algorithm, we find the median of n array, right? Now we reduce to smaller 1/3 of the n elements, right? Yeah. The median. We just look at all the medians. So the problem size is reduced to 1/3 of the original elements. Can we call median algorithm recursively on these 1/3 of the element? We call recursively, okay? All right. Recursively, and we assume M, the median is in the middle. We arrange median in the middle, okay? All right. 2 elements to its left should be smaller than the median, and the 2 elements to its right should be greater than the median, but not sorted. The whole thing not sorted. We find the median, and then we know what are those elements smaller than the median, what are those elements greater than the median. Okay? Yeah. So we arrange data in that way. Now, yeah, remember, this median may not be the overall median, right? Yeah. Okay? Yeah. May not be the overall median. Yeah. All right. All right. Okay? All right. So then, what are those elements that are definitely smaller than the median? Can you see these elements must be smaller than this median, this one? Yeah. Based on the work we have done, based on the work, yeah? Because lower part less than its corresponding median, but the corresponding median less than the central median, right? The central median, all right? Similarly, can you see these elements must be definitely greater than the median? Right? Yeah. Those 2 parts, definitely less than the median, definitely greater than the median, that corresponds to the left subarray and the right subarray. Center element, this median somewhere between. So that's the split the original array into subarrays such that our split not too biased, okay? Not too much biased, yeah. Because we have a cushion, left-hand side cushion, right-hand side cushion, okay? The split must be somewhere in the middle. So not extremely biased like that. N of 2 sides. That's extremely biased. So those cases would cause the worst case efficiency. Now we avoid extremely biased cases, and we put 2 reasonable cushions at the 2 sides, so the split will be, good enough. Will be good enough. Yeah. So then when we do recursion, we want to make sure the element we want to look at, not too close to the end. In that way, we can get a good efficiency for the selection problem. Okay? So the result, still a lot of detail. I cannot get there, yeah, because too complicated. Yeah, too complicated. Yeah. So the result we can get big theta of m, linear. So any linear problem can be solved by an algorithm with this big theta of m efficiency, linear algorithm. Okay? Yeah. You just know this result. So actually, that can be solved by a C constant times m, number of comparisons. There is a C constant you need to do. Okay? Yeah. C times n. Yeah. That C should be smaller than 16. Yeah. So you can improve that C. Yeah. But there is one you can do in 16. 16 times n. Yeah. But it's still a linear algorithm. Okay? Yeah. Yeah. So that's the information I want to let you know about the general selection problem. Okay? Without giving you the whole algorithm. Very good. Yeah, but if you try that hard, you can understand. Well, this class I can be quiet. Yeah. Okay? Yeah. Yeah. It's in our textbook. Yeah. All right. All right. Then I like to use a few more minutes to talk about an interesting and useful case, special case problem. Find the median of 5-element array. We haven't done that, right? Find the median of 5 elements. It's pretty challenging, yeah, but not too bad. Yeah. We did a sort 5-element array. Do you still remember we did a sorting 5-element array? Do you still remember how many comparisons we need sorting 5-element array? 7. The optimal solution is 7, sorting 5-element array. After you sort, can you pick the median immediately? Yeah. So that means 7 comparisons is a little more than the minimum number of comparisons for finding the median of 5-element. Yeah. Here the question. Here, we want to find the median of a 5-element array. Okay? Better than 7 comparisons. Okay? Because our goal better. Because the sorting result. Yeah. Sorting result. Yeah. Yeah. All right. Yeah. Okay. Yeah. So let's try. Yeah. Yeah. Here what we can do, we can use 6 comparisons to do it. Our target is 6 comparisons. Yeah. All right. So here our goal, 6 comparisons. Yeah. So let's see how to do it. Yeah. How to do it. Yeah. Actually, I give you part of the work in some previous assignment. Yeah. Yeah. I give you part of the work in a previous assignment. Yeah. So if we put several, at least 3 questions together, we get it. Okay? Yeah. So let me review those 3 questions. Yeah. So you will see. Yeah. We're almost there. All right. First, yeah, let me use 3 steps. The first step, tournament method. Remember the tournament method? We do comparisons with tournament method. Tournament method. Okay? Yeah. Here we consider our array with 5 elements, x1, x2, x3, x4, x5. Okay? Yeah. Let's arrange them, comparison, the tournament. x1, x2, and they do comparison, and we assume x1 is the winner without loss of generality. Okay? Yeah, we can assume that for simplicity. When we compare x3 and x4, we assume x3 is the winner without loss. Okay? All right. This is our first comparison. This is our second comparison. Okay? Then, comparison between x1 and x3, let's assume x1 is the winner. That is our third comparison. Okay? So the first 3 comparisons, we to get this result. Yeah. Now we want to clean up our data. Yeah. After the first round, we want to organize our data to try to explore some useful properties. Then we want to do elimination. Okay? All right. So the tournament method. Step 2, elimination method. The idea is, can we use the information collected from the first step to help us eliminate some of the elements for consideration in the second step? Okay? Yeah. Here, let me draw the diagram. Yeah. Diagram. So we want to see the data relationship. Okay? x1 greater than x3 and greater than x4. Right? Yeah. x1 also greater than x2. And we have x5 unknown relationship. We don't know any information about x5. Okay? All right. Here, can you see which element cannot be the median so we can eliminate it? Can you see any element in this diagram? It can never be the median, so we can safely eliminate it. Which one? X1. Because x1 is greater than 3 elements. Okay? The median has rank 3. Okay? If you count from left, it's third. If you count from right, also third. But this x1 already greater than 3 elements. So it is among top 2. x1 is among top 2. So we can safely eliminate it. Gone. Gone. Okay? We take away x1 from the consideration. Yeah. To find a median, we never need to look at x1. Okay? All right. Then, to find a median, we only need to consider the remaining 4 elements. Yeah. Now, update. Now we need to do update. The original median, our goal, find original median. The original median in the remaining 4 elements. Can you give me the rank number for the original median? If you count from right, what's the rank number? From right. Second. So the original median, so here, okay, yeah. Original median equals second largest remaining, okay? In the remaining 4 elements. Okay? All right. Did we calculate second largest a few times in our several assignments? Yeah? We know how to calculate second largest, right? And here, you already know x3 greater than x4, so you do not need to compare x3 and x4, but you can compare x5 and x2, right? Oh, sorry. Oh, what's wrong? Yeah, excellent. Yeah. But you can compare x2 and x5, right? x2, x5, then one is smaller, one is larger, okay? Yeah, yeah. So you can assume x5 smaller, okay? Yeah. You can assume x5 smaller, you know, because, you know, symmetric. If 5 larger, x2, you know, just the other way around, okay? Then, all right, so here, this is, you compare x2 and x5. This is comparison number 4, okay? Comparison number 4, all right. Comparison number 5, you compare, so here, yeah, let me, step 3, okay? Step 3, find second largest remaining, okay? In the remaining, okay? After exclusion, after elimination, okay? All right. So x2 here, x5 here, without loss of generality. Yeah, this is comparison number 4, okay? All right. x3 here, x4 here. All right. Then comparison number 5, you know, if you write 3, you know, yeah. Comparison number 5, all right. x3 greater than. Then the last comparison, which 2 elements you want to compare to get a second largest? Yeah. x3 is the largest. Yeah. So last comparison, which 2 you want to compare? x2 and x4. The winner would be the median. This is number 6. Because this one you can exclude, all right? This one you can exclude. Because this one already less than x2. How can it be the second largest, right? Yeah. Another way we look at this, another way, because x3 is the remaining largest. When you compare second largest, we only look at those elements that are direct loser of the winner. Direct loser. Indirect loser, you do not need to look at. Indirect loser, they already lost to other elements, right? How can they be the second largest? They already lost to other elements. So we only pick direct loser from the winner. So here, direct loser, x2 is a direct loser of the winner, okay? x4 is a direct loser of the winner. So we compare. So here, the idea is this comparison. So we compare the direct losers of the winner. Winner, we know it's the largest, okay? Okay? Direct loser for the second largest. That's the, you know, the way right way to do it. Okay? Yeah. So this, you can see, after these 3 steps, we find the median of 5 elements. Now you know the answer, with total 6 comparisons. With total 6 comparisons. Okay? Yeah. All right. Any question? Any question? Yeah. Everyone must understand the solution. Okay? It's very important. Everyone must understand. Yeah. Because we will have a few derived questions from now on. Yeah? Derived questions. Based on this one, derived questions. Okay? Yeah. Here, let me give you first derived question right here and see if you can get it. Yeah. Just apply the result here. Okay? All right. Okay. You know it. This is the result. Apply it. Okay? All right. The first derived example, I use this small space to talk about it. Yeah. Given 100 elements array, 100 elements. Yeah. We want to find an element. Find one element in it. The condition, not in top 2. This element cannot be in top 2 and not in bottom 2. How to find that element? Not in top 2, not in bottom 2. How many comparisons do you need? 2. 6. Okay. Yeah. Can you see? Everybody can see it. We can use 6 comparisons to find that element. Given 100 elements, okay? We want to find one that is not among top 2 and not among bottom 2. Okay? Yeah. We did similar questions before, right? We select arbitrary 5, okay? Then we find the median of the 5 elements. You use 6 comparisons. That median cannot be in top 2, right? Because already less than 2 elements. That median cannot be in bottom 2, right? Already greater than 2 elements. Yeah. This is, I'll give you an example. This is what I call derived question. Okay? The question based on our existing result. But you have to be familiar with our existing result. Then I can derive many questions like that. Okay? Yeah. All right, so get ready for those derived questions. Okay? Yeah. All right, yeah, so we have a little more than 15 minutes. I may talk about a small topic in introduction to that merge sort. Yeah. So the next time we work on the algorithm. Today, I talk about the motivation. Why we need to do the merge sort, the motivation part. Okay? Yeah. Introduction to merge sort. Yeah. Yeah. I just do 2 slides for introduction. All right, yeah. Okay. Problem number 13, merge 2 sorted arrays. Yeah. We are given 2 sorted arrays. Yeah. If you look at our midterm question number 25, last one, 2 sorted arrays, right? Yeah. But here we merge 2 sorted arrays. Given 2 ordered arrays, how to merge them to get an ordered array? It's simple, but we want to use the fastest possible way to merge them. Yeah. It's simple solution, yeah, but it's useful. Yeah. So this relatively easy computing problem, it is useful. Yeah. All right. So let's look at that. Motivation. Yeah. Now let me describe why we want to do this. Okay? Yeah. Yeah. There are many different reasons. Here I just select one special example to show you it's useful. All right. So what's that example? Motivation. Why we need to consider this problem. Yeah. Yeah. All right. Question. Here, I give you a special question here. How to sort a huge array. Yeah. How to sort arrays, you have no problem. Yeah. There are several algorithms you can run. But here, I give you a special situation. This array, the data is huge. How large it is. Yeah. How large it is. Yeah. You can only store the data on your hard drive, and this array is so big, you cannot load all the array elements into the main memory at the same time. That large. Your main memory, how large is our main memory? Yeah. Think about that. Okay? Yeah. 8 gigabyte or 16 gigabytes, right? Yeah. Right now, so for your laptop, do you know how large is the memory size of your laptops? Yeah. I estimate about 16 gigabytes, right? Yeah. Most of you 16. Some of you probably 8. Yeah. So my laptop, yeah, smaller than yours. Yeah. My laptop about 8 gigabytes. Yeah, because the special one. Yeah. Yeah. So your 16 gigabytes, because I want to buy, yeah, but later I feel, yeah. Yeah. So think about, suppose your memory has the 16 gigabyte size, but our array size is larger than 16 gigabytes. Can you sort that array? Suppose you have an array size 20 gigabytes. You cannot load at the same time 20 gigabytes into your main memory. How can you execute your algorithm, right? Yeah, think about it. Yeah. Here, the answer is we can do it. We use our 16 gigabyte memory, main memory computer. We can sort 20 gigabyte array size of data. No question. Yeah. The idea is simple like this. Yeah. Load the whole array into the main memory. Can you load subarray, part of your data subarray? We do not load the whole array. Yeah. We only load the subarray. If you can load, you can choose appropriate size subarrays to be loaded into the main memory. Can you sort the whole array? Yes, you can. Yes, you can. Okay? Yeah. You just you need to do the input output, that operation frequently. Copy data in, do some operation and copy data out. All right? Yeah. Do things like that. Okay. Here we need to use merge operations. If you can do merge operations, then you can do that sorting without loading all the data into your main memory. Okay? Here, let me use the simple diagram to describe this idea. Yeah. All right. I use this line segment to represent the whole array, yeah, with greater size than your memory size. Yeah. All right. Now, let's do divide and conquer. Well, when we sort it, first let us divide it into several smaller subarrays such that each subarray can be loaded into the main memory. How about that? Okay? Each subarray can be loaded into the main memory. So we have enough memory space to manipulate the data. in main memory. So we can sort it in main memory for that subarray. One by one. Can we do one by one? One after another. Okay? After we complete sorting the first subarray, we kick it out. Then load the second subarray in and sort it, then replaced by third subarray, and so on. After that, we get all the subarray ordered. Can we do that? Okay? Yeah, we can do that. Okay? All right. After that, in order to get the whole array ordered, do we need to do the merge operation? Merge two adjacent subarrays? Yeah. Now you can see we need to use this merge operation. Ordered subarrays. Okay? But when we merge two ordered subarrays, copy data, you do not have to load two subarrays into the main memory at the same time. Every time, you just load a portion of the subarray. Then you do merge operation, yeah. So you copy to your destination location. Then every time you load a portion of the subarrays. Then you do comparison, you put in place in your destination subarray. You can reserve the destination location. Okay? Yeah. So you copy, organize the data, order the data to your destination. All right. So here you can see after several merge operations, can you merge the first two to get one whole ordered array? After that, can you merge next two? Finally, can you merge last two to get a whole array sorted? Yeah. That's the idea. Okay? Yeah. This special situation. Okay? Yeah. So, sometimes when you have limited resource, your computing resource is limited. So you have to find a way to get around the bottleneck. Because your data, you have to split your data. Okay? And process them portion by portion. Yeah. Not as whole. Too much resource required. That much. Solve individual subproblems. Merge. Okay? Yeah. All right. How to merge two sorted arrays. Yeah. All right. Yeah. Yeah. So here we have this motivation thing. Next, we need to look at the initial ideas to merge two ordered arrays. Given two arrays that are already sorted, how to get a new sorted algorithm, a new sorted array that contains all the elements. Yeah. Excuse me. Yeah. The solution is pretty straightforward. Yeah. Not very complicated. Yeah. Very intuitive. Yeah. Yeah. All right. Take advantage of the structured data. That order is important. Okay? That order is important. Yeah. All right. Do not use any sort that does not make use of any other information. Yeah. Yeah. Because we know sorting is pretty expensive. Don't run any sort algorithm. It's pretty expensive. And you want to use some comparison that based on the order information. That information is important. You need to take advantage of that. All right. Selection sort does not take advantage of the order information, right? The data is ordered or unordered. The selection sort give you the same result. Okay? Yeah. Bubble sort does not take advantage of the order information. Okay? Yeah. Ordered, unordered, you get the same result. Okay? All right. Then, insertion sort. Insertion sort closely related to the order. Yeah. If the data is ordered, you get a best case, and then that best case is much better than the worst case and the average case, other cases. Yeah. So that means the insertion sort, that idea is useful here. We should borrow some of the ideas from the insertion sort, because that one takes advantage of the order information a lot. Yeah. Yeah. So we should start from there, insertion. So let us recall our insertion operation a little bit. Then we try to generalize for our merge operation, insertion operation and the merge operation. We try to connect them, these two operations. All right. Yeah. Yeah. So we know insertion sort is very good for almost sorted array. Yeah. Very fast for almost sorted array. Yeah. Yeah. All right. Yeah. Then, take a different view on insertion step. Now we need to look at insertion again, but this time we want to use a new view to understand it. New view, understand it. Okay? So this is the beginning of our next story. So let me do it next time. Because in order to make the whole story complete, it's a beginning, okay? So let's, because we do not have many minutes left. So let's start from this point next time. All right, so that's it.